Hello and welcome. In this video, we will explore the crucial role of data structures and algorithms in shaping modern systems. We will uncover how a strong understanding of these core concepts is essential for designing scalable, efficient, and robust applications. Let's begin by defining how data structures and algorithms form the backbone of any system. Let's delve into the key data structures and algorithms concepts essential for system design. Data structures refer to efficient ways of organizing data that enable optimal storage, retrieval, and manipulation, especially crucial in distributed systems. Algorithms are step-by-step procedures that solve specific problems, forming the core of system operations and optimization. Time and space complexity are critical measurements that determine system performance, scalability, and resource utilization at scale. Optimization techniques refer to methods to enhance performance through caching, parallel processing, and distributed computing. Now we'll see the practical applications of arrays and hash tables in real-world system design scenarios. Arrays are used in time series data storage, suitable for storing monitoring metrics, logs, and system events chronologically. Arrays are used as in-memory buffers, which serves as temporary storage for batch processing and message queues. Arrays are also used for sharding, which helps in distributing data across multiple nodes using array indices. Here's a simple code snippet for time series data storage. Hash tables are useful in caching for fast lookups of database query results, API responses, and computed values. Hash tables help in load balancing using consistent hashing to distribute requests across servers. Hash tables are also useful in database indexing, offering fast, order-of-one lookups for key-value stores and NoSQL databases. Here's the code for a simple LRU cache implementation. Let's see how trees and graphs are used in system design. Trees are used in database indexing like B-trees and B+ trees for efficient database query optimization. Trees are useful in storing hierarchical data like in file systems, organizational structures, and category management. Trees are also useful in decision systems by creating decision trees for routing, classification, and recommendation engines. Here is a visual representation of a B-tree. Graphs are used for representing network topology, which show system components and their connections. Graphs are also useful in path finding, which helps in finding optimal routes in distributed systems and service mesh. Graphs are helpful in modeling social networks between users, content, and interactions. Here is the Python code for graph representation in a system. Next, we will explore the applications of queues and stacks in distributed systems. Queues are used in message brokers for decoupling services with asynchronous communication, such as with Kafka or RabbitMQ. Queues are also used in task scheduling for managing job processing in distributed systems. Here is the visual representation of a queue. Here is the Python code for a task queue in a distributed system. Stacks are used in function call stack for managing execution context in serverless architectures. Stacks also help in undo operations by tracking state changes for rollback capabilities. Here is a visual representation of a stack. Here is the Python code for transaction rollback using stack. Let's see how sorting and searching algorithms are used in distributed systems. Sorting is used in log analysis for processing and organizing massive log data in time order. Sorting is also useful in big data processing with MapReduce frameworks for sorting petabytes of data. External merge sort divides large datasets into smaller chunks, sorts each chunk independently, and then merges the sorted chunks. This algorithm takes order of n log n time and order of n space. Here is the Python code of distributed sorting with MapReduce. Searching is useful in search engines to find relevant documents across distributed indexes. Searching helps in content delivery by locating the nearest cache for requested content. Distributed binary search partitions data across nodes, with each node performing local search on its portion of the data. This algorithm takes order of log n time and order of k nodes where k equals number of partitions. Here is the Python code of distributed search implementation. Dynamic programming optimizes complex problems by breaking them into simpler subproblems, storing solutions to avoid redundant calculations. In distributed systems, this approach enhances efficiency and resource utilization. DP can be used in resource allocation. This helps in optimizing server resources, container placement, and workload distribution across data centers using DP to find the most efficient allocation patterns. DP is also useful in caching strategies. This helps in implementing intelligent caching policies like LRU, least recently used, and LFU, least frequently used, with DP to optimize cache hit ratios and minimize latency. Here's the code of server resource allocation and dynamic content caching. Now let's talk about how you can use data structures and algorithms for scalability and performance. Horizontal scaling helps to add more machines to distribute load and increase system capacity. Consistent hashing helps in load distribution. Graph algorithms helps for optimal partitioning. Distributed caching strategy is used to cache data across multiple nodes to reduce latency and database load. LRU least recently used and LFU least frequently used caching with hash tables help in this. Bloom filters help for cache optimization. Data partitioning divides data across multiple databases or servers to improve throughput and manageability. Range-based partitioning with B-trees and hash-based partitioning for load balancing helps in this. Microservices architecture builds modular, independently deployable services to enable scalability and development agility. Graph algorithms for service discovery and queue-based communication patterns help in this. Let's examine some real-world case studies where data structures and algorithms play a critical role. In search engine indexing, to build a search engine capable of indexing billions of web pages and returning relevant results in milliseconds, we can use inverted indexes using hash tables for mapping terms to documents, with B-trees for efficient range queries and distributed hash tables for partitioning the index across thousands of servers. PageRank algorithm, a graph algorithm that scores web pages based on the number and quality of links to them. Uses adjacency lists to represent the web as a directed graph. For real-time recommendation systems, to provide personalized content recommendations in real time based on user behavior and preferences, we can use min-hash and locality-sensitive hashing for efficiently finding similar users and items, and priority queues for maintaining top-in recommendations per user with order login updates. Collaborative filtering uses sparse matrices and nearest neighbor algorithms to identify patterns in user preferences and recommend similar content in sublinear time. To summarize, here are some key takeaways from our discussion. Data structures and algorithms fundamentals are the building blocks of scalable, efficient distributed systems. Time and space complexity considerations are critical at scale and directly impact system performance. Modern system designs optimize for both horizontal and vertical scaling, using appropriate data structures. And finally, trade-offs between different data structures and algorithms must be evaluated in the context of system requirements. Understanding how to apply data structures and algorithms concepts to system design challenges enables engineers to build more robust, scalable, and efficient distributed systems. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.